Today we are going to discuss about what are the things and what are the technologies that are required to build a quantum computer. Okay, before going on to the concept, I wanted to give some brief explanation from the past how this quantum computer or the name quantum has been evolved. So in 1980s, okay, scientists started realizing that our universe doesn't behave classical. Okay, so doesn't behave classical. Tiny things like atoms and electrons behave very differently. They can be in many states at once. So this is called superposition. Okay. So a normal classical computer cannot handle or simulate these behaviors easily. Okay. Even if you try to simulate a small molecule, the computer runs out of memory because there are too many possibilities to calculate. So then Richard Feynman, a very famous physicist, said that if nature itself quantum, if nature itself is not classical, if nature itself is quantum, why should our computers be classical? That is the question he has given. Okay. That one idea started a revolution. So if we make computers that work using the same principles as atoms and photons, we could understand nature directly. So that's how idea of quantum computing was born. Okay. So moving on to before going on to the requirements, but what is quantum computer? A quantum computer is a new type of computer that works using quantum mechanics. That is nothing but the science of very tiny particles. So in normal computers, we'll be using bits, that is nothing but 0 and 1. But whereas in quantum computer, data is stored in qubits, okay, which can be both 0 and 1 at a time. So it can be written as ket psi is equal to alpha ket 0 plus beta ket 1. So where alpha square plus beta square is equal to 1, you already know. Because of this property, quantum computers explore many possibilities at once. So instead of one by one, like classical computer, it has the power to compute many possibilities at once. So the quantum computers are useful for molecule simulation. That is nothing for new medicines. Okay, for new medicines. Okay, whereas this breaking cryptography is nothing but solving very hard problems. Okay, so whereas optimization problems is nothing but finding the best ways for our choice quickly. Okay, finding best ways or best possible choices quickly. Okay, so that is what about quantum computer. Now moving on to the requirement of Divincenzo, the famous scientist Divincenzo from IBM in 2020 in 2001. Sorry. So let's start off five golden rules. So I will explain what are those five golden rules for building a quantum computer. So Divincenzo in 2001 listed five golden golden rules to build quantum computer. Okay, so these are the building checklist. Okay, so first one is scalable qubits. So we should be able to make more qubits without losing control. So you know the types of qubits, so we can make some stable qubits that can be like without losing the control. Okay, second one is nothing but initialization. So in we must start all qubits in non-clear state. Okay, for example, initially we'll start all qubits with ket 0. Okay, and now third one is nothing but long coherence time. So qubits must stay stable long enough to perform the operations. Okay. The fourth one is nothing but universal quantum gates. Okay, we need a small set of basic operations that can perform any calculation using universal quantum gates. And the last one is nothing but, this is very important, qubit measurement. So we must be able to measure each qubit correctly to get output. So later two more rules were added to quantum communication. So that is nothing but conversion between stationary and flying qubits for communication. Okay, conversion between stationary and flying qubits for communication. It is used for quantum communication. And the last one is nothing but send flying qubits from one place to another place. That is nothing but, it will be used for quantum internet. Okay, so this is for quantum communication and this is for quantum internet. Now I will explain very quick recap of all those things one by one. Okay, we must build qubits that can be increased in number without problems. Okay, that is the increase in number without loss in control, we can say. So every qubit should be real and controllable like ions. So these are nothing but controllable qubits. So be stable. Every qubit should be stable even when we add more. Okay, when we add up one plus so on, they should be stable. So every qubit should be work in the same way for small and large systems. So they need to work collaboratively. So example is nothing but, here I can say IBM and Google use superconducting circuits. Okay, IBM and Google use superconducting circuits or superconducting qubits. Okay, they already control hundreds of them. Okay, whereas IonQ uses trapped ions and which are more stable but slower. So scalability means the system can grow 10 to 100, 100 to 1000 without losing control. Okay, that is about without losing control. Okay, that is the main agenda of this scalability. Now moving on to the second requirement. Okay, before we start any quantum program, every qubit must start in known position only. That is nothing but usually get 0. If qubits start randomly, the answer will be randomly too. So if it starts randomly, we'll get some random answers that may not suit for our outcome. So to fix this, so two superconducting qubits are cooled close to absolute 0. Okay, that is nothing but using cooled to ground state. So they automatically fall to their ground state. So one more thing, trapped ions are reset with laser or microwave pulses. Okay, so these is like setting all counters to 0 before starting the race. So these set to get 0 initially. Okay, for our requirement. So that is the second requirement, that divisions have been derived. That is what the meaning of the second requirement. So moving on to the third requirement. So if you see here, coherence means the qubit remembers its quantum information without any disturbance from the environment. If it forgets that, we call it as decoherence. We compare, okay, we compare two times, that is nothing but T coherence is nothing but how long the qubit can stay stable, and T operation is nothing but how can the operation can be. Okay, so we need this condition. Okay, we require this condition. That means the qubit must stay long enough to do thousands of operations before it forgets. Okay, before it forgets. That's why quantum computers are kept extremely cold and isolated from any disturbance. So that is the reason we require ultra cold temperature, that is nothing but 15 millikelvin, and they should be isolated. Okay. And moving on to one more requirement, that is nothing but a universal set of quantum gates. Already I have discussed what are the quantum gates. So Hadamard gate creates the superposition, you already know. Phase gate changes the internal angle of the qubit. Okay, and C0 gate links two qubits, that is nothing but entanglement. Okay, that you need to remember. So that is the fourth requirement. Now moving on to the fifth requirement. After the program runs, we must measure the qubit. So when measuring the qubit, okay, the qubit chooses either 0 or 1 because it may lose its superposition state. So for example, superconducting qubits are read by detecting the current. Okay, okay. So trapped ions emit light if they are in certain state. Okay, trapped ions emit, that is something but fluorescence detection. Okay, without proper measurement we can't understand what result that computer has found. So proper measurement is required for quantum computers. So moving on to one more thing is nothing but bonus requirements. I have explained some bonus requirements. So these are for quantum communication and quantum networking. So sixth one is nothing but convert between stationary and flying qubits. Stationary is nothing but ions or superconductors are processing. Okay, but whereas in flying we'll be using photons, that is used for communication. Okay, now the requirement 7 is nothing but sending the flying qubits between places. So we'll be using optical fiber, okay, and repeaters or satellite. This is the base of quantum internet. This is the base for quantum internet. So these two make long distance quantum communication possible. Okay, these two are the latest requirements. So now we are moving on to the basic components of quantum computers. So initially I said we require qubits. So you know what are the types of qubits. Okay. So and the second one is nothing but quantum gates. So we require quantum gates to operate the pulses, everything. Okay. We'll be operating quantum gates using microwave or laser pulses, and will perform quantum operations by rotating states on the Bloch sphere. Okay. Now the coherence and decoherence are the important components in quantum computer. Okay. Now that is nothing but the main concept comes quantum error correction. I have made a video on this, so please refer that video for your understanding. So quantum error correction is nothing but bit flip error and phase flip error will be there in quantum error correction. So this is required. Okay, cryogenic system is nothing but it requires very cool temperature. Okay, that is nothing but near minus 273 Celsius. So and control and measurement system should be very good. Okay, for functional quantum computer, and we require quantum software algorithms for this. So programming languages like Qiskit IBM developed by IBM, and Circuit developed by Google, and QHash developed by Microsoft run algorithms such as Shor's algorithm, Grover's algorithm, okay, in quantum software. So this is about the components. So now challenges. Already you know, if there is no coherence we cannot perform the operation. So that the main challenge is nothing but decoherence and error rates. So we'll be having some quantum errors. Okay, and the temperature should be absolute zero or near 0 Kelvin. Okay, and even small disturbance can disturb qubits. So noise is one of the main challenge, and scalability, thousands of qubits controlling is very hard. Okay, that is the thing. That is, these are all the challenges that we face in quantum computers. So now I'm moving on to some real world progress that we are achieving in quantum. So IBM quantum uses superconducting circuits. Okay, scalable and stable, whereas Google quantum AI achieved quantum supremacy in 2019. Solved a task classical computers that couldn't do. So IonQ and Honeywell, okay, use trapped ions, okay, with very long lifetimes. Okay, very long lifetime. Xanadu and PsiQuantum used photons for future quantum networks. So every company is slowly checking off divisionzo list. Okay, they are following this divisionzo requirement, then only they are performing all those operations. Okay, moving on to the future of quantum computing. So we require fault tolerant quantum communication, that is nothing but error free operation. So we require quantum internet, so linking quantum computers worldwide. So that is the reason we require quantum internet, and we require the integration of quantum with artificial intelligence for smart hybrid systems. So in the coming 10 to 20 years, quantum computers will change. In medicine, they will discover new drugs. In climate, weather modeling, weather forecasting with accurate prediction. Okay. In security, we'll be using cryptography. In industry, we'll be using logistics and optimization. So quantum computing is not just technologically, but it is a new way of understanding and using the nature. That is what scientists say. Okay, if you are having any doubts, let me know. So thank you guys.